Black holes have become the celebrities of space. They swallow stars, bend light, and stretch time itself. Every year they dominate headlines as if they're the most dangerous things the universe has ever created. They're not. Some objects can release more energy in a single second than our sun will produce over its entire lifetime. Others are so massive they pull entire galaxies toward them. One region of space is so empty that astronomers still struggle to explain how it formed, and one discovery may force us to rethink whether our understanding of the universe is even complete. The frightening part isn't that these things exist, it's that we've already found them. Every discovery in this video comes from observations made by NASA, the European Space Agency, the James Webb Space Telescope, the Hubble Space Telescope, and decades of peer-reviewed astronomical research. We'll begin with a star that's escaping our galaxy forever, and end with a place so enormous and so mysterious that some scientists still debate whether modern cosmology can fully explain it. If you're enjoying this journey through the universe, make sure you subscribe. Every documentary on this channel is built from real observations, scientific research, and the discoveries that remind us how little we truly know about the cosmos. With your support, I can keep bringing these stories to life. My goal is to reach 1,000 subscribers before September. Now, let's see what comes next. Let's begin. Number 10. Hypervelocity Stars. At first glance, there's nothing unusual about them. They're stars like countless others scattered across the Milky Way, burning hydrogen, producing light, and living out lives that can last billions of years. If you looked at one through a telescope, you wouldn't immediately know you were witnessing one of the fastest natural objects in our galaxy. Because stars aren't supposed to leave. Everything inside the Milky Way is held together by gravity. From the smallest asteroid to the largest star clusters, nearly everything orbits the galaxy's center. It's a cosmic dance that has continued for more than 13 billion years. Hypervelocity stars broke that rule. The first confirmed example was discovered in 2005. It was moving so quickly that astronomers realized the Milky Way could never pull it back. Its journey had become permanent. So what could launch an object weighing hundreds of thousands of times more than Earth to such incredible speeds? The answer begins 26,000 light-years away. At the center of our galaxy lies Sagittarius, a star, a supermassive black hole containing roughly 4 million times the mass of our Sun. Imagine two stars orbiting each other like dancers. As they drift closer to Sagittarius, a star, gravity becomes increasingly violent. Eventually, the black hole tears the pair apart. One star spirals inward, disappearing forever. The other is hurled outward like a stone released from the world's most powerful slingshot. Some reach speeds exceeding 1,000 kilometers every second, fast enough to escape the Milky Way completely. To appreciate how extraordinary that is, imagine firing a rocket from Earth. Escape velocity lets it leave our planet, but escaping an entire galaxy is something else entirely. It's like throwing a baseball so hard it leaves not just the stadium, but the continent. And once it does, there's no coming back. If planets orbit that runaway star, and many astronomers believe some probably do, they're coming along for the ride. Picture a civilization living beneath its night sky. Generation after generation, the familiar band of the Milky Way slowly grows smaller. Millions of years pass. The spiral arms fade. Eventually, their home galaxy becomes nothing more than another distant smudge among billions. Not because it disappeared, because they left. Astronomers have now identified dozens of these stellar exiles, and new discoveries continue to emerge as telescopes become more powerful. They're proof that even entire solar systems can be evicted from galaxies. One close encounter, one impossible acceleration, and a star spends the rest of eternity alone between galaxies. But at least astronomers understand what launched these stars. The next object doesn't need to travel anywhere. It simply exists. And if one appeared anywhere near Earth, our entire planet would notice within seconds. Number 9. Magnetars. If hypervelocity stars are the fastest escape artists in the galaxy, magnetars are its most violent survivors. At first, they don't look extraordinary. They're no larger than a city, just 12 to 20 kilometers across, smaller than many metropolitan areas on Earth. Yet, inside that tiny sphere is more mass than our sun. Imagine crushing an object nearly 1.5 million kilometers wide into something small enough to fit inside a single city. Matter itself begins behaving in ways that feel almost impossible. A single teaspoon of magnetar material would weigh billions of tons. But incredible density isn't what makes astronomers fear them. It's what surrounds them. Every magnetar generates a magnetic field, unlike anything else in the known universe. Earth has one. It's the reason compasses point north and why our atmosphere survives the constant bombardment of charged particles from the sun. The sun has one, too. Even ordinary refrigerator magnets produce one. A magnetar simply takes the concept and pushes it beyond imagination. Its magnetic field can be more than 1,000 trillion times stronger than Earth's. Numbers like that are difficult to picture. So astronomers use comparisons instead. If a magnetar passed halfway between Earth and the Moon, it wouldn't need to touch us. Its magnetic field alone could erase every credit card on Earth. Bring it closer, and the electronics inside satellites would begin failing. Closer still, the atoms inside your own body would no longer behave normally. Fortunately, no known magnetar exists anywhere near our solar system. The closest confirmed examples are thousands of light years away. And that's good news, because magnetars don't remain quiet. Every so often, the immense magnetic stress twisting their crust becomes too much. The surface cracks, not like an earthquake, more like the entire star briefly rearranging itself. The result is called a giant flare. For less than a second, a magnetar can release more energy than our sun will produce over hundreds of thousands of years. On December 27, 2004, astronomers witnessed one of these eruptions. The flare originated from a magnetar roughly 50,000 light-years away. Despite that enormous distance, the burst still affected Earth. Spacecraft temporarily lost the ability to measure the event because the radiation overwhelmed their detectors. Our atmosphere itself became slightly ionized, not because the star was close, because the explosion was simply that powerful. Imagine standing on Earth, feeling the effects of an object 50,000 light-years away. Now imagine if it happened much closer. Fortunately, the universe is unimaginably large, and magnetars are thankfully rare. Astronomers estimate only about 30 have been confirmed in the Milky Way, although many more almost certainly remain hidden. Each one is a reminder that the universe doesn't always need black holes to unleash extraordinary power. Sometimes, a dead star is enough, a sphere no bigger than a city, a magnetic field stronger than anything humanity has ever encountered, and an explosion powerful enough to briefly disturb a planet halfway across the galaxy. But even magnetars are still stars. The next object isn't a star at all. It's a world with no sun, wandering through the darkness completely alone. Number 8. Rogue planets. Every planet you've ever heard of has one thing in common. They belong somewhere. Earth circles the sun. Jupiter follows its familiar path every 12 years. Even the distant worlds beyond Neptune remain bound to our solar system, held in place by gravity that has existed since the planets first formed. That's what planets are supposed to do. They orbit stars. Rogue planets don't. Somewhere between the stars are worlds with no sunrise, no sunset, no parent star to call home. They're drifting through the galaxy completely alone. For centuries, astronomers believed this shouldn't happen. Planets are born inside enormous disks of gas and dust surrounding young stars. As gravity pulls material together, those disks slowly become worlds. The assumption seemed obvious. If a planet forms around a star, it should stay there. Then, astronomers began finding evidence that some didn't. Computer simulations revealed a violent possibility. Young planetary systems are chaotic places. Massive newborn planets constantly tug on one another. Their gravity reshapes entire solar systems, pushing smaller worlds into unstable orbits. Sometimes those encounters end peacefully. Sometimes one planet receives a gravitational kick so powerful that escape becomes inevitable. Not from a single planet, not from the solar system, from its own star, forever. Imagine Earth suddenly accelerating beyond the sun's reach. Within days, daylight would disappear. The oceans would begin freezing. Plants would die. Temperatures would continue falling for thousands of years. Our planet would become a frozen world, drifting through eternal darkness. That's the fate astronomers believe countless rogue planets have already experienced. Some may have once looked remarkably similar to Earth. Others could be giant worlds larger than Jupiter. Either way, their skies are permanently black. For decades, rogue planets remained mostly theoretical. They were simply too dark to see. Planets don't produce their own light. They reflect starlight. Take the star away, and the planet becomes almost invisible. So how do you find something that barely emits any light? You don't look for the planet. You watch what it does to everything behind it. Einstein predicted that gravity bends light. When a rogue planet drifts between Earth and a distant star, its gravity briefly magnifies that star's light before moving on. The event lasts only hours or days. Then it's gone. No warning. No second chance. Astronomers call this gravitational microlensing. It's one of the few ways to detect worlds that refuse to reveal themselves, and the discoveries have been surprising. Some studies suggest rogue planets may be nearly as common as stars themselves. Think about that. The Milky Way contains hundreds of billions of stars. If those estimates are even close, our galaxy could contain hundreds of billions of lonely planets wandering through interstellar space. Entire worlds, invisible, silent, passing between the stars without anyone noticing. But perhaps the strangest question isn't how many exist. It's whether some could still support life. At first, that sounds impossible. Without sunlight, every planet should become a frozen wasteland. Yet some scientists have proposed another possibility. A sufficiently massive atmosphere could trap heat escaping from the planet's interior. Radioactive elements deep underground continue producing energy for billions of years. Hidden beneath kilometers of ice, liquid oceans might survive. No sunlight, no blue sky, no familiar seasons. Just darkness stretching forever above an ocean that has never seen a sunrise. If life exists there, it would never know what a star looks like. A planet without a sun, an ocean without daylight. A world that has spent millions of years wandering through the emptiness between galaxies' brightest lights. But even rogue planets were once part of a normal solar system. The next object shouldn't exist at all. Because according to everything astronomers thought they knew, a star and a dead star were never supposed to become one. Number 7. Thorne Żytkow objects. Most stars live predictable lives. Small stars slowly burn their fuel before fading into white dwarfs. Massive stars explode as supernovae, leaving behind neutron stars or black holes. Astronomers thought they understood the cycle. A star is born. It lives. It dies. Simple. Then two physicists asked a question that sounded almost absurd. What would happen if a neutron star fell inside another star without destroying it? At first, the idea seemed impossible. A neutron star is one of the densest objects in the universe. It packs more mass than our sun into a sphere barely 20 kilometers wide. If something that dense plunged into an ordinary star, common sense says the collision should rip both objects apart. Instead, the mathematics suggested something stranger. Imagine two massive stars orbiting each other for millions of years. Eventually, the larger one explodes. What's left behind is a neutron star. The companion survives for a while. As the second star grows older, it expands into a red supergiant. Its outer layers swell outward until they engulf the neutron star. At first, the neutron star continues orbiting, hidden inside its companion. But space isn't empty anymore. It begins plowing through dense stellar gas. Every orbit creates friction. Every orbit steals energy. Slowly, the neutron star spirals deeper toward the center, until one day it reaches the core. Now something extraordinary exists. From the outside, it looks like an ordinary red supergiant, huge, red, slowly pulsating. Exactly the kind of star astronomers have observed for centuries. But inside, instead of a normal stellar core, there's a neutron star, a dead star, living inside another living star. Astronomers call this bizarre hybrid a Thorne-Żytkow object, named after physicists Kip Thorne and Anna Żytkow, who first described the possibility in the 1970s. For decades, they remained purely theoretical. No one knew whether nature actually made them. Then, astronomers found a candidate. In 2014, researchers studying a red supergiant known as HV 2112 noticed something unusual. Its light contained chemical signatures that didn't fit normal stellar models. Elements like lithium, rubidium, and molybdenum appeared in unexpected amounts. Those are exactly the kinds of elements theory predicted might be created if a neutron star were hiding inside. The discovery made headlines. Had astronomers finally found one? Not everyone was convinced. Other researchers argued the observations could be explained another way. New studies questioned the original measurements. Even today, the debate continues. That's what makes these objects so fascinating. They're balanced between theory and observation. Possible, plausible, but not yet proven beyond doubt. Imagine standing on a planet orbiting one. You'd see an enormous red star filling the sky. Nothing unusual, nothing threatening. No sign that beneath hundreds of millions of kilometers of glowing gas, one of the densest objects in the universe was buried alive. The star would look completely ordinary. Its secret would remain invisible. A stellar giant hiding a collapsed star at its heart. A cosmic nesting doll. One star inside another. But at least if Thorne-Żytkow objects exist, astronomers know roughly what they're looking for. The next object doesn't hide inside a star. It outshines entire galaxies. And for years, scientists couldn't explain how anything in the universe could possibly become that bright. Number 6. Quasars. For thousands of years, humanity believed the brightest objects in the night sky were stars. Then, we built better telescopes. And suddenly, the universe became much brighter than anyone thought possible. In the early 1960s, astronomers noticed strange points of light scattered across the sky. They looked exactly like stars. Small, sharp, motionless, nothing unusual. Until scientists measured how far away they really were. The results made no sense. These weren't stars inside our galaxy. They were billions of light years away. At that distance, they should have been far too faint to see. Yet they shined brighter than entire galaxies. Something wasn't adding up. Imagine looking across the Pacific Ocean and seeing a single candle burning on the opposite shore. That's impossible. The light would never reach you. Yet somehow, these tiny points were visible across billions of light years. Astronomers gave them a name, quasi-stellar radio sources, eventually shortened to quasars. For years, nobody knew what they were. Some believed they were a completely new type of star. Others thought the measurements had to be wrong. Because if the distances were correct, nothing in physics should produce that much energy. Then, astronomers looked closer. At the center of nearly every large galaxy sits a supermassive black hole. Normally, those black holes remain relatively quiet. They consume the occasional cloud of gas or wandering star, but otherwise hide in darkness. A quasar forms when that changes. Imagine a black hole suddenly surrounded by enormous amounts of gas, dust, and shattered stars. Instead of falling straight inward, the material begins spiraling around the black hole like water circling a drain. As it does, the gas accelerates faster and faster. Collisions become violent. Temperatures climb into the millions of degrees. The swirling disk begins glowing, not because the black hole emits light, because everything around it is being heated to extraordinary temperatures. Before the material disappears forever, it releases an astonishing amount of energy. The result is a beacon visible across much of the observable universe. One quasar can outshine every star in its galaxy combined. Not hundreds, not thousands, hundreds of billions. And some remain active for millions of years. To appreciate that scale, imagine replacing the sun with a quasar. Earth wouldn't simply become hotter. Our planet would cease to exist. Long before the radiation reached us, the solar system itself would be sterilized. The light alone would be overwhelming. Fortunately, the nearest known quasar lies hundreds of millions of light-years away, far enough that its incredible brightness becomes little more than another faint point in the night sky. But astronomers have found something even stranger. Some quasars existed less than 1 billion years after the Big Bang. That shouldn't have been enough time for their central black holes to grow so enormous. Yet there they were, already containing billions of times the sun's mass. How? Did black holes grow faster in the early universe? Were they born unusually massive? Or is there something about the first galaxies that modern astronomy still doesn't understand? The James Webb Space Telescope is now beginning to uncover new quasars from the universe's earliest history. Each discovery raises more questions than answers, because every new quasar appears to challenge our timeline of cosmic evolution. They're not just bright, they're inconvenient. They force astronomers to revisit ideas that once seemed settled, a black hole surrounded by light brighter than an entire galaxy, a beacon shining across billions of years, and a mystery that's only becoming stranger as our telescopes improve. But even quasars are tied to individual galaxies. The next discovery doesn't belong to just one galaxy. It appears to be pulling thousands of them toward something astronomers still can't fully see. Number 5. The Great Attractor. Every galaxy is moving, not just spinning, not just expanding with the universe, actually moving through space. For most of human history, we assumed galaxies simply drifted apart as the universe expanded after the Big Bang. Edwin Hubble's observations in the 1920s seemed to confirm exactly that. The farther away a galaxy was, the faster it appeared to be receding. It looked orderly, predictable, until astronomers noticed something disturbing. Our own galaxy wasn't following the pattern. Neither were hundreds of others. Instead of simply moving away with the expansion of the universe, they were drifting sideways, all toward the same region of space. At first, researchers suspected a measurement error. Maybe the distances were wrong. Maybe the telescopes needed calibration. But every new survey revealed the same thing. Galaxy after galaxy, cluster after cluster. They were all moving in one direction, including us. The Milky Way isn't standing still. It's racing through the universe at roughly 600 kilometers every second. That's more than 2 million kilometers per hour. And we're not traveling alone. The Andromeda Galaxy, the Virgo Cluster, hundreds of nearby galaxies, all appear to be falling toward the same invisible destination. Astronomers eventually gave it a name, the Great Attractor. Not because they knew what it was, because they didn't. Imagine standing on a hill and watching thousands of rivers flowing in the same direction. You don't need to see the ocean to know it's there. Something enormous must be pulling them. That's exactly what astronomers saw. Entire galaxies behaving like rivers of stars, converging toward a destination hidden from view. So why couldn't they simply point a telescope at it? Because the Great Attractor lies almost directly behind the center of the Milky Way. Between Earth and that mysterious region are billions of stars, enormous clouds of dust, and thick bands of gas that block visible light. Astronomers call this region the zone of avoidance. For decades, it lived up to its name. We knew something was there. We just couldn't see it. As technology improved, scientists began using radio waves, infrared telescopes, and X-ray observations to peer through the dust. What they found wasn't a single object. It was an enormous concentration of galaxies, galaxy clusters, superclusters, an immense web of matter stretching across hundreds of millions of light years. And yet, even that wasn't enough. The visible galaxies couldn't account for all the gravity. Something else had to be contributing. Dark matter almost certainly plays a major role, perhaps enormous amounts of it. Invisible, undetectable directly, yet massive enough to influence the motion of entire galaxy clusters. Then, the mystery became even stranger. As astronomers mapped larger portions of the universe, they realized the Great Attractor might not be the final destination after all. It appears to be moving towards something even larger. Far beyond it lies an unimaginably vast concentration of galaxies known as the Shapley supercluster, one of the most massive structures in the nearby universe. Some researchers believe much of the Great Attractor's pull is actually part of an even larger cosmic flow leading toward Shapley. In other words, the thing pulling hundreds of galaxies may itself be getting pulled. Imagine watching every airplane in the world flying toward one airport, then discovering that airport is flying toward another continent. The deeper astronomers looked, the bigger the mystery became. Today, scientists have a much better understanding of the region than they did decades ago, but they still can't fully explain every motion observed across our local universe. Gravity on this scale becomes incredibly difficult to untangle. Entire superclusters influence one another across distances so vast that light itself needs hundreds of millions of years to cross them. Our galaxy, every star you've ever seen, our sun, Earth, even you, are all passengers on a journey toward a destination measured not in miles, but in galaxy clusters. A gravitational current carrying hundreds of millions of stars through the cosmos. But even the Great Attractor is made of something astronomers can observe. The next entry is different. It outweighs every visible galaxy in the universe. Yet no telescope has ever seen it directly. Number 4. Dark matter. Everything you've seen so far has one thing in common. Astronomers can observe it. Hypervelocity stars emit light. Magnetars unleash bursts of radiation. Rogue planets reveal themselves through gravity. Quasars outshine entire galaxies. Even the Great Attractor can be traced by mapping the galaxies surrounding it. The next entry breaks every one of those rules. It has never been photographed, never been touched, never been detected directly. And yet, without it, the universe we see today couldn't exist. Astronomers call it dark matter. The name sounds mysterious, but it isn't a poetic nickname. It's a confession. It literally means, we don't know what this is. The story begins nearly a century ago. In the 1930s, Swiss astronomer Fritz Zwicky studied a massive collection of galaxies known as the Coma Cluster. He measured how quickly the galaxies were moving. The numbers didn't make sense. They were traveling far too fast. According to everything astronomers knew, the cluster should have flown apart billions of years ago. There simply wasn't enough visible matter to hold it together. Zwicky proposed an extraordinary explanation. Most of the cluster's mass wasn't visible at all. Something invisible was providing the missing gravity. Almost nobody believed him. The idea sounded too strange. For decades, it remained little more than a curiosity. Then, in the 1970s, astronomer Vera Rubin pointed her telescope toward ordinary spiral galaxies, including galaxies much like our own. She wasn't looking for dark matter. She was simply measuring how stars moved. The expectation seemed obvious. Planets closer to the sun orbit faster than planets farther away. Mercury races around the Sun. Neptune moves much more slowly. The same pattern should exist inside galaxies. Stars near the center should orbit quickly. Stars near the outer edge should move much more slowly. But they didn't. The outer stars were moving almost as fast as the inner ones. Again, the math refused to cooperate. If only visible stars and gas existed, those galaxies should have torn themselves apart long ago. Instead, something unseen was holding everything together. Imagine spinning a merry-go-round faster and faster. Eventually, everyone holding on would be thrown off. Now imagine thousands of people remaining perfectly in place, even though you can't see what's keeping them there. That's what astronomers observed across galaxy after galaxy. The invisible became unavoidable. Today, nearly every measurement points in the same direction. Galaxies rotate too quickly. Galaxy clusters contain too much gravity. Even light itself bends around invisible concentrations of mass. One of the most dramatic examples came in 2006. Astronomers observed two enormous galaxy clusters colliding in what is now called the bullet cluster. The hot gas from both clusters slammed together and slowed down, but the majority of the gravity didn't. Using gravitational lensing, scientists discovered that most of the mass passed straight through the collision almost untouched. The visible matter stayed behind. The invisible matter kept going. It was one of the strongest pieces of evidence that whatever dark matter is, it behaves very differently from ordinary matter. So what is it? That's the question. Some scientists believe it's made of entirely new particles that have never been detected on Earth. Others suggest primordial black holes. Some propose completely new physics. Decades of experiments have searched deep underground, inside particle accelerators, and even beneath mountains. So far, nothing. No detector has definitively found a dark matter particle. No laboratory has confirmed its identity. And yet, the evidence for its gravity continues to grow stronger. Current estimates suggest that everything you've ever seen, every planet, every star, every galaxy, every nebula, every black hole, accounts for only about 5% of the universe. Dark matter makes up roughly 27%. The rest is something even stranger. Think about that. Imagine walking into a library containing 100 books. 95 of them are locked inside invisible boxes. You can't open them. You can't read them. You only know they're there because the shelves bend under their weight. That's our universe. Everything humanity has ever observed is only a tiny fraction of what's actually out there. Invisible galaxies of gravity surrounding visible galaxies of light, an unseen framework holding the entire cosmic web together. A substance that outweighs every star we've ever seen, yet remains completely unknown. But even dark matter isn't the biggest mystery in the universe. The next entry isn't invisible because we can't detect it. It's terrifying because there is almost nothing there at all. Number 3. The Boötes Void. Space is unimaginably empty. Even inside our own solar system, the distances are almost impossible to comprehend. Light from the Sun takes more than 8 minutes to reach Earth. Neptune orbits nearly 4.5 billion kilometers away. And that's considered crowded. Between the stars are trillions upon trillions of kilometers of emptiness. Between galaxies, even more. Astronomers accepted that. The universe isn't evenly packed. Some regions contain thousands of galaxies. Others contain only a handful. Gravity naturally creates a vast cosmic web with enormous filaments of galaxies surrounding immense empty spaces. Those empty regions are called cosmic voids. Most are hundreds of millions of light years across. They're fascinating, but they're expected. Then, astronomers found one that shouldn't exist. In 1981, while surveying distant galaxies, astronomer Robert Kirshner and his team noticed something unsettling. A huge section of the sky appeared almost empty. At first, they assumed the survey was incomplete. Perhaps the telescopes hadn't looked deeply enough. Maybe distant galaxies were simply too faint to detect, so they kept observing. The emptiness remained. The region eventually became known as the Boötes Void, named after the constellation in which it appears. Calling it large doesn't do it justice. The Boötes Void stretches roughly 330 million light-years across. To understand that scale, imagine replacing our entire Milky Way with a single grain of sand. Now step back until that grain sits inside a football stadium. You're still nowhere near understanding the size of this void. More than 2,000 Milky Ways could fit side by side across it. If you traveled through the void at the speed of light, the fastest speed anything can move. The journey from one side to the other would take 330 million years, not days, not centuries, hundreds of millions of years. And during much of that journey, you might not encounter a single galaxy. The observable universe contains billions upon billions of galaxies. The Boötes Void contains remarkably few. It's not completely empty. Astronomers have identified a small number of galaxies scattered within it, but compared to the surrounding universe, it's astonishingly barren. Imagine flying over an enormous city, then suddenly reaching a region the size of an entire country, containing only a few isolated houses. You wouldn't just ask who lives there. You'd ask why the city was never built. That's exactly what astronomers asked. How does something this empty form? According to modern cosmology, galaxies grow where dark matter creates an invisible framework. Gravity slowly pulls gas together, stars ignite, and over billions of years, enormous galactic structures emerge. The Boötes Void appears to have missed much of that process. Some simulations suggest it formed as smaller voids merged together over cosmic time. Others argue that ordinary gravitational evolution can eventually produce such enormous empty regions. But even today, the Boötes Void remains one of the largest and most striking examples ever discovered. Standing inside it, if such a thing were possible, would change your view of the universe forever. Our night sky is beautiful because we're surrounded by stars. Even the faintest patches contain distant galaxies. Inside the Boötes Void, the darkness would be overwhelming. Imagine looking in every direction and finding almost nothing. No glowing spiral galaxies, no brilliant clusters, just isolated islands of light separated by distances so vast they would barely break the darkness. It wouldn't feel like being in space. It would feel like being outside the universe itself. The Boötes Void reminds astronomers that the cosmos isn't simply a collection of galaxies. It's also defined by what's missing. Sometimes, nothing can be just as important as something. A region so vast that light needs hundreds of millions of years to cross it, a place where galaxies become rare, and a reminder that even after mapping millions of them, the universe still contains enormous blank spaces. But even the Boötes Void is something astronomers can map. The final entry is different. It isn't a place. It isn't an object. It's a force driving the entire universe apart. And without it, everything you've seen in this countdown would exist in a completely different cosmos. Number 2, dark energy. By now, the universe should be slowing down. That was the expectation. The Big Bang happened nearly 13.8 billion years ago, launching galaxies in every direction. Gravity immediately began fighting back. Every galaxy, every cluster, every star added its own tiny pull to the universe, working together to slow the expansion. Imagine throwing a ball into the air. It rises quickly at first. Then gravity begins stealing its speed. Eventually, it stops. Astronomers expected the universe to behave the same way, not because anyone had proven it, because it seemed inevitable. The more matter the universe contained, the harder gravity should pull. For decades, scientists argued over only one question: how quickly was the expansion slowing? Nobody seriously expected the answer they found. In the late 1990s, 2 independent teams of astronomers began studying a special type of exploding star called Type 1 A supernovae. These explosions are remarkably consistent. Each one reaches almost exactly the same brightness. That makes them perfect cosmic measuring tools. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it must be. The teams expected to measure a universe gradually losing speed. Instead, the distant supernova appeared dimmer than predicted. There was only one explanation that fit the observations. They were farther away than they should have been, which meant the universe hadn't been slowing down. It had been speeding up. The discovery stunned astronomy. Imagine throwing a ball into the sky. You watch it climb. Instead of slowing, it suddenly accelerates upward all by itself. That's impossible, unless something else is pushing it. That's exactly what the universe appeared to be doing. Something invisible, something powerful, was overcoming gravity itself. Astronomers called it dark energy, not because they understood it, because they didn't. The name simply acknowledged the mystery. Whatever dark energy is, it appears to fill the universe. Unlike gravity, which pulls objects together, dark energy seems to push space itself apart. Not galaxies moving through space, space expanding between galaxies. That's an important distinction. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they're crawling across the rubber, but because the rubber itself is stretching. The universe behaves in a remarkably similar way. Every second, the distance between galaxy clusters grows. Every second, the observable universe becomes larger, and every second, the expansion accelerates. Today, astronomers estimate that dark energy makes up nearly 68% of everything in the cosmos. Think about what that means. Visible matter, everything you've ever seen, accounts for about 5%. Dark matter contributes another 27%. The remaining majority, the largest component of the entire universe, is something humanity still cannot explain. It dominates the cosmos. Yet no one knows what it actually is. Some physicists believe dark energy is an intrinsic property of empty space itself. Others suggest new quantum fields filling the universe. Some propose that our understanding of gravity breaks down over the largest cosmic distances. There are even theories suggesting dark energy isn't constant at all, that it may slowly change over billions of years. Each possibility carries profound consequences, because the future of the universe depends on the answer. If dark energy remains constant, galaxies will continue drifting farther apart until the night sky grows almost completely dark. Billions of years from now, future civilizations may look into space and see only their own galaxy. Every other galaxy will have expanded beyond the observable universe. The evidence for the Big Bang itself could disappear from view. If dark energy becomes stronger, the expansion could eventually overwhelm gravity entirely. Galaxy clusters would separate. Galaxies would dissolve. Solar systems could be torn apart. Even atoms might not survive. Astronomers call this hypothetical ending, the Big Rip. It's only one possibility, but its existence reminds us how little we truly know about the force shaping the universe's future. A force we cannot see, a force we cannot touch, a force that outweighs everything humanity has ever observed, and a reminder that the biggest mysteries in science aren't hiding inside black holes. They're woven into the very fabric of space itself. Black holes may dominate headlines, but they're only one chapter in a universe filled with phenomena that challenge our understanding of reality. A star escaping the Milky Way forever. A dead star with a magnetic field powerful enough to affect a planet from across the galaxy. Worlds wandering through eternal darkness without a sun. A star hiding another dead star inside its core. Black holes bright enough to outshine entire galaxies. A gravitational current pulling hundreds of galaxies through space. invisible matter outweighing every star we've ever seen. A void so vast it makes entire galaxy clusters seem insignificant. And finally, a mysterious force accelerating the expansion of the universe itself. Perhaps the most unsettling discovery isn't any single object on this list. It's what they all reveal together. The more powerful our telescopes become, the more the universe surprises us. Every mystery we've solved has uncovered even larger questions waiting beyond it. And that may be the most terrifying truth of all. Not that the universe is dangerous, but that after centuries of exploration, we may have only begun to understand it. Number 1, the observable universe. Every object on this list has something in common. It exists somewhere. A magnetar occupies a single point in space. A rogue planet drifts through the galaxy. A quasar sits at the center of a distant galaxy. Even the Boötes Void has boundaries. The final entry isn't one object. It's everything. Everything humanity has ever seen. Everything we've ever measured. Every galaxy, every star, every planet, every black hole. Every atom that has ever been observed exists inside something astronomers call the Observable Universe. The name sounds straightforward, but hidden inside it is one of the strangest ideas in modern science. Notice the word observable, not the universe. The observable universe, because those two things aren't necessarily the same. Imagine standing in the middle of a vast forest at night. You switch on a flashlight. The beam illuminates the trees around you. Beyond the light, the forest continues. You simply can't see it. The observable universe works the same way. Light travels at a finite speed, about 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single second. Yet even light has limits. The universe is approximately 13.8 billion years old. That means there hasn't been enough time for light from infinitely distant regions to reach us. Everything we can observe lies inside an enormous cosmic horizon. Beyond it, light is still traveling. Imagine receiving a letter mailed billions of years ago. Now imagine waiting for another letter. That won't arrive for another 100 billion years. That's the scale astronomers are dealing with. The edge of the observable universe isn't a wall. It isn't the end of space. It's simply the farthest distance from which light has had time to reach Earth. And here's where the story becomes even stranger. If the universe is 13.8 billion years old, shouldn't the observable universe have a radius of 13.8 billion light years? It doesn't. It's roughly 46.5 billion light years in every direction. How is that possible? Because while light has been traveling toward us, space itself has continued expanding. Imagine an ant walking across a rubber band. While the ant moves, someone stretches the rubber band. The ant travels forward, but its destination keeps moving away. That's exactly what has happened to ancient light crossing the universe. By the time that light reached Earth, the galaxies that emitted it had already moved unimaginably farther away. As a result, the observable universe spans approximately 93 billion light years across. And that's only the part we can see. Astronomers have no evidence that the universe ends there. In fact, most cosmological models suggest it continues far beyond our cosmic horizon. How much farther? Nobody knows. It could be hundreds of times larger, millions of times larger. It could even be infinite. The truth is, we don't know. Everything humanity has ever discovered, every spacecraft we've launched, every equation we've written, every telescope we've built, has explored only this tiny, visible bubble. Think about that. Imagine taking a glass of water from the Pacific Ocean. Now imagine trying to describe the entire ocean using only that single glass. That's effectively what we're doing with the observable universe. The farther we look into space, the farther back in time we see. The James Webb Space Telescope has already revealed galaxies that formed only a few 100 million years after the Big Bang. Each new observation pushes our cosmic horizon a little deeper, not because the universe is growing, because our understanding is. And every discovery raises the same unsettling possibility. If the observable universe is only a fraction of everything that exists, then most of reality remains forever beyond our reach. There may be galaxies whose light will never arrive, stars we'll never witness, civilizations we'll never know existed, not because they're hidden, not because they're too faint, but because the universe itself expands too quickly for their light to ever reach us. No technology can overcome that limit. No future telescope can change it. Some parts of the cosmos are permanently inaccessible, not because of engineering, because of physics. The observable universe is the greatest map humanity has ever created. Yet every edge of that map carries the same silent message. Beyond this point, we simply don't know. Hypervelocity stars, Magnetars, rogue planets, Thorne Żytkow objects, Quasars, the Great Attractor, dark matter, the Boötes Void, dark energy, and finally, the observable universe itself. Each one reveals a different side of the cosmos. Some demonstrate unimaginable power, others reveal astonishing emptiness. And a few remind us that the greatest mysteries aren't the things we've discovered, they're the things we haven't. For centuries, every new telescope has promised answers. Instead, it has given us even bigger questions. Perhaps that's the most humbling truth in all of astronomy. The universe has never become less mysterious, only larger, and somewhere beyond the edge of everything we can observe. The next great discovery is already waiting.